Hello, and welcome back to the driving seat of neural networks. And we discussed that neural networks are essentially more complex than other simpler models like support vector machines. There are some parallels that are interesting to think about, but a neural network has essentially a much larger number of hyperparameters, and it has certain difficulties when you're trying to use that for a practical problem in terms of generalization, especially. So it's important to understand what each of these buttons do and how should we choose them. So once we have taken a look at the backpropagation algorithm, we are now in a position to move on to this more serious step of analyzing the impact of different parameters and how we to choose those. So an MLP has, or a multi-layer perceptron, or a fully connected neural network, or a backpropagation neural network. Those are all different names for the same thing in our discussion. It has a large number of parameters. You can specify how many layers you have, how many hidden layers you want, how many neurons within each layer you want, what is the activation function of each neuron. You can have rectified linear activation functions, you can have log sigmoid activation functions. You can also change how these neurons connect to each other. So far, we only talked about different types of neural networks that have a very rigid structure that each neuron in one layer is connected to all neurons in the next layer. But you can also have other types of connectivities. So that's also a hyperparameter. And that changes the architecture or the representation of the neural network. And that's also something to but I'm just putting it out there. You can have different types of loss functions depending upon the type of problem that you are trying to solve. You can have mean square error, entropy, hinge loss. You can have different type of regularization as well. We haven't done that in any of the models that we've studied so far, but you can enforce different types of regularization like L1, L2 on the weights in the neural network. Similarly, you can use different type of optimization methods. You can use stochastic gradient descent. You can use adaptive gradient descent with momentum. There are other methods like Levenberg-Marquardt optimization or RMS-prop. And your weight initialization, where you initialize the neural network, is going to also have an impact. So how do we figure out all of this in the neural network? Now, one thing that is really important to understand is that in a support vector machine or the linear models that we talked about earlier, we had a convex or a linear activation. We had a linear function W transpose X that given an input generated a prediction score that was linear. We had an error function that was also convex, hinge loss, for example, or a square error, right? And so the whole thing was convex, and the resulting optimization problem was convex. And what that means is that as we had discussed before, it's whenever you use gradient descent on that, you're guaranteed to have convergence. So you always end up at the global minima because there is only one of them, right? There are no local minima in the optimization surface. Things are not so rosy when we talk about neural networks because you have these nonlinear activation functions, and those may or may not be convex, and your resulting and the loss function you may use may not be complex. The connectivity of your neural network may also nullify any convexity. So you may end up in your optimization landscape with local minimas. So if you plot, for example, if you have a neural network with only two weights, let's call them W1 and W0 and W1, apologies. And if you plot for a given value of W1 and W0 and W1, you would have a certain value of error, right? If for this value of, let's say we pick W0 equal to 0 and W1 equal to minus 20, for a given data set, you're going to end up with a certain value of the error, right? If you pass that example with those weights, it's going to produce an output. You compute that error, you average it across all of those training examples, and you end up essentially with an error figure that is plotted on the y-axis. So this surface, or error surface as it is called in neural network, or the loss landscape of neural networks, is typically not convex. So if you cannot, if you use gradient descent, for example, you may or may not converge depending upon where you start. What we want is, first of all, we want optimization. We want to estimate those parameter values based on our for training data set, so that we can end up with good weight values that at least are able to classify the training data set. Now, that is, as we had discussed earlier, optimization is a necessary requirement for learning to take place, but it's not a sufficient one. but at least it's a necessary one. So first we need to ensure that the neural network is trainable. The loss converges. This is the most important thing. Whenever you're making a neural network, it's really important that you analyze what is the loss value or how does it change across epochs. This plot that I call the convergence plot, in which you plot the x or the value on the x-axis, the epochs on the x-axis or iterations on the x-axis, and the loss value on the y-axis, it should ideally be going down over the training data set, right? Once we have that good convergence, then we can start thinking about whether it generalizes or not. And we're going to have to see how to ensure convergence of neural networks, given that the loss surface is not convex. Okay, so there are a number of tricks we can use. To understand those tricks, we need to step back into the derivation of the weights that we have done. We don't need them for trying to run neural networks, but to ensure that these converge, or why a neural network is not converging, or to debug the convergence of a neural network, we need to understand these things. So I'm going to walk you through this real quick. Remember, the optimization process of a neural network works like this. You have a neural network that has a number of weights for the hidden layer and weights v. You feed it an example x, it generates an output y. For a given output, you already know the target, you compute the error, and then you feed back that error to update your neural network, right? The weights v and w. And we had worked out these equations that how much change is needed in order to minimize this error using gradient descent. We had derived these equations from delta w, and we had computed the weight update equation for weights in the weights of the links that connect the input features to the hidden layer neurons. So those are v's, and then we had these w's. If you are having trouble remembering this, I welcome you to go back and take a look at the structure of the neural network that we had been talking about. But essentially what we have over here is an expression that tells us how much weight should I change to minimize a certain error using gradient descent. And it had all of these terms, right? We had these deltas, and then we had all of this. But if we substitute everything that we substitute a value of delta, we know that delta j is simply delta in j multiplied by f dash, which is a derivative of the activation function for the given input or the net input into the jth neuron z in j. And we know that delta nj has this expression, and then we had this zj, which can be expressed like this. If we plug everything into this equation, back into this equation over here, then we get this nasty looking expression. It looks really complex, right? And the goal is not for you not to remember this, but to understand what it actually means. So what it actually means is, for a neuron that has two layers, essentially a layer of weights from the input to the hidden layer of neurons, and then from the hidden to the output, like so we have a two-layer MLP, and this is the weight update for one of those weights. Now this is how much you need to change that weight in order to reduce that error. So you'll be doing this over multiple times throughout your training cycle, right? But if you look at it, this change in weight is proportional to the input value, xi. So if this xi is equal to 0, then we'll not have any change in this weight. And because there won't be any change in the weight, there won't be any learning taking place. We'll not be able to optimize because the weights aren't changing. Similarly, we have this derivative term. This delta w value is proportional to this derivative or the gradient of the activation function. So if the gradient of the activation function is 0, we'll still end up with no weight updates. And that's what we really need to understand. What we want to do is we want to train a neural network. And what that essentially means is that we don't want the network to stop learning prematurely. We want it to stop learning once the output of the neural network, which is given by this expression or this y value, matches the target that we have. When y matches t, we have achieved our goal. We don't want to change the weights anymore, at least for this given example, right? But other than that, anything that changes or that sets this delta v to 0 is stopping us from learning. So it doesn't allow us to update our weights, and we are going to understand what those things are that can impede learning or can impede optimization. We have already spotted one. If your net input feature value is 0, your weight update is going to be 0. If the gradient of your activation function is going to be 0, so this is the gradient of the activation function for this particular input. If the gradient of your activation function for this input is 0, your weight update is going to be 0. Similarly, if these weights are 0, these wjks are 0, then this whole thing becomes 0, and then you end up with no weight updates again. Similarly, if you have this value over here, this derivative is 0, you again get no weight updates. So I think you should be able to see a pattern now. What we are looking for are ways that can impede our learning, that can make these weight updates to be 0 when we don't want them to be 0. We do want them to be 0 when the target, or TK in this case, matches the output of the neural network. That's when we want it to be 0, because that is when we have achieved our goal. But other than that, that's not good, right? And that's what we're going to try to do. When should the neural network weight update be 0? It should be 0 when the target matches the output of the neural network, which is y for a given input. If this is equal to 0, we want it to be equal to 0. And if you see in this equation that if the target matches the output, every output matches the corresponding target value, we essentially end up with a 0 weight update, which is what we want, right? Otherwise, we should be updating weights. And what in this equation can make this weight update go to 0? If xi is equal to 0, if f dash is equal to 0, so that can happen if the derivative of the activation function becomes 0. So the derivative of an activation function should not become 0. And when do derivatives become 0? Derivatives become 0 when we have a function like this and we are in a region. So let's say if we have a function like this. This is f of x. And let's say we have x on this axis. This is the net input. This is the input to this activation function. So don't think this is an example. This is just, I want to denote this activation function. Okay, and this is the input to the activation function. If the input to the activation function is over here, then you can see that we are in a relatively flat area of this activation function, where the derivative is now going to be very small or close to 0. So that is called a saturation region of this particular activation function. So our activation functions should not saturate, because if they do saturate, then we end up with these derivatives being 0. Okay, that's not good. If wjk are equal to 0, so if you start with wjk equal to 0, then your weight update delta v is going to be 0, so no weight update is going to take place. So that lesson from that is that don't start with 0 weights. But at the same time, if your net input into the activation function is very large, and that can happen if the weights are very large or if your input is very large. Remember, for a single neuron, what happens is that it takes in inputs, multiplies each one of them with the corresponding, let's say we have d inputs, or we're using n in this case, so we have n inputs. Each one is getting multiplied with the corresponding weight, and then we do a summation, right? We sum wi x I, right? And we can do it for I is equal to 1 or I is equal to 0 to n in this case. That becomes our net input into this neuron. And then we apply an activation function on top of that to produce our output, right? So that is the output of this neuron, a single neuron in this case. Now if you look, if the weight value is very large, and if the x value is very large, then this summation is going to be very large. And for very large activations, if you are using a sigmoidal activation function, like the one that I have plotted in front of you, you can end up in this saturation region. And that is going to push the derivative, this derivative equal to 0, and your weight update is going to become 0. So when an input is too large in magnitude, either positive or negative, it pushes you into the saturation region of your activation function. So that is not a good idea. When weights are too large, similarly, we shouldn't have too large weights to begin with. If you have too many layers, so let's say if you have one layer, or if you have one hidden layer, you see that there is a product of derivatives going on. There's a derivative over here, and then there is a derivative over here. So there's a product of derivatives going on. So if one of those derivatives is going to be small, or if both of those derivatives are going to be small, their product is going to be even smaller. That's simple arithmetic, right? And your weight update is going to be smaller. And as you increase the number of layers in a neural network, there are going to be more of these product terms coming in. So you are going to have a problem that is called the vanishing gradient problems in deep networks. That is when you have very small gradients for a single layer, because these gradients are in multiples of one another, they're being multiplied with one another, you end up with these weight updates that are even smaller. And that's what is called vanishing gradients. An opposite effect can also happen. If your gradient values are very large, then what's going to happen is this is large and this is large, and your weight update is going to be very large, and that's going to make a substantial change to your weights. Your weights become large, and in the next iteration, what's going to happen is because you have large weights, you are going to be pushed into the saturation region of your activation function, and your weight updates are going to again become small. So this is called an exploding gradient problem, but essentially it results in the vanishing gradient problems down the line as well. So these are the things that we need to watch out for. We shouldn't be doing these things, otherwise we are there to jeopardize the training process or the optimization process of our neural network. And that's what we are going to achieve. How to improve the convergence of a multi-layer perceptron? The first thing that we need to make sure is that we need to ensure that we use a good weight initialization. We don't want to start with zero weights. We don't want to start with large weights. And it has an implicit effect on regularization as well. If you start with very large weight values, then it's not regularized as well. Remember regularization? So this is going to have an impact on that regularization bit as well. So over here, we are going to take an example of solving the exclusive OR problem. If I initialize my weights randomly, if I initialize them to zero, it's going to take even longer number of epochs for it to converge to a certain error value over the training data set. If you use random weights, we take 2,891 iterations to solve this binary exclusive OR problem. The binary exclusive OR problem is something that you've already seen. You have 0, 0, 0, 1, 1, 0, and 1, 1. There are two features, and you have got a single target output, which is 0, 1, 1, 0. So this is the first feature, this is the second feature, and this is the target value, right? So this is the problem. So when solving this problem using a multi-layer perceptron with random weights, you spend 2,891 epochs. But if you initialize your weights a bit better using a procedure called Goin-Widrow, it's available in most libraries. And if you use that, you can converge really fast. You can converge within like 2,000 epochs, right? So that's good. Note that once you have zeros in your input representation, right? When the input representation has zeros in it, you can have low weight updates, right? So if we simply change the bipolar optimization problem, the binary exclusive OR problem, in which we have 0, 0, 0, 1, 1, 0, and 1, 1, with the corresponding targets of 0, 1, 1, 0. If we change that problem to simply bipolar labels, in which we have -1, -1, -1, 1, +1, -1, and -1, and +1, +1, with the corresponding targets being -1, +1, -1, and +1 and -1. So converting this bipolar representation to this binary representation into this bipolar representation actually helps you improve your prediction performance significantly. So when you use the binary representation with the Goin-Widrow optimization, you have about 2,000 epochs. But if you simply change this input representation, you significantly reduce this. You use only 387 epochs, and you have this. If you use Goin-Widrow, you end up doing the same thing in 224 epochs. Similarly, if you use a sigmoid activation function, which looks like this, if you plot it, right? We've seen plots of sigmoid activation. You see that there are regions over here that this is going to be -1 and this is going to be +1. So whenever I use this when I am in this region, it pushes me into the saturation region of this activation function. So if I change the target values, instead of being -1 and +1, if I change them to be -0.8 and +0.8, this simple change actually halves the number of activations, the number of epochs that I require for convergence. Okay, so you can use these tricks. Okay, so ideally we should be using non-saturating or slowly saturating activation functions. So don't use such activation functions like sigmoid ones if you have a deep network especially. Okay, so what we want to have is an activation function whose derivatives never go to zero. One such function is this tan sig an activation function, or you can have a leaky relu activation function, or you can have what is called an elu activation. They're all available in your PyTorch library. Okay, I'm not making these names up. And you can even learn your own activation function. We have a paper on it if you want to read about it. But the choice of the activation function has an impact on how you end up, how many epochs are required. So rectified linear works most of the time, but if you have deeper networks, you may want a non-saturating activation function that does not have zeros in the in the in its representation. Okay, so you can look at the gradients of these activation functions, and you can see that for a sigmoid activation function, which is shown in this red color over here, its gradient goes to zero, and that prevents learning from taking place whenever you have a net input that is in this range. Okay, so you can change that. Let's say if you can simply improve your activation function by using log transformations as well. You can also optimize, you can get better optimization procedures, such as you can use momentum-based weight updates, and that is what Adam does, the activation function, sorry, the optimization function that we use. So think of it like this. You have a function that you want to optimize, right? You are over here right now, and you want to take a step down the slope. You have a certain value of alpha, right? Alpha, and you move a certain amount on this axis. So you update your weights by a certain amount. But as you can see, this is a pretty stable region of the slope. So that means I should be okay to take a larger step. And that is what this momentum step does. And that is what is implemented in Adam. So you can end up with much faster convergence. You can also create artificial examples. There are other ways that we're going to talk about, such as drop-off or patch normalization. But what I want you to do as a home exercise is I want you to take the exclusive OR example, the code that you've been given for multilayer perceptrons, and try out these various variants of multilayer perceptrons and understand how each of those design choices or representation choices affects your number of epochs. Okay, so see what is the effect of different parameters on the convergence characteristics, how many networks, how many layers you need, how many neurons in each layer, and so on. Try to play with this if you want to really get a hang of it. There's a really good book called Neural Networks Tricks of the Trade that essentially talks about even more tricks about how you can improve the generalization performance as well as the training speed of your neural networks. Thank you.